few details about P4 and how you can do high-performance packet processing with it. How many of you are familiar with P4? Okay, so that's good. There's a few. Let's quickly dive into the presentation. This is about putting the network owners and the people who are building the networks in the driving seat. So far, high-performance networking has been held hostage to a certain extent by fixed function switches. The reason being, fixed function switches have a certain amount of protocol logic baked into it, and that's the only function that they can do, or those are the only protocols they can do. Let's say a new packet processing protocol comes into being, you really can't run that protocol at line rate in that fixed function switch because it's not designed to run those protocols. And so what happens is when you're building a network and if you start with a fixed function switch, you have to kind of look at what that fixed function switch can support and then write your control plane software for it and then deploy it in your network. And so you're kind of constraining your network to the functionality of that fixed function switch that you've built your top of rack switch or your spine switch from. This actually puts the vendor of the fixed function switch in the driving seat because you're dependent on that silicon. Now consider a world where you have a high performance programmable switch ASIC. So what this can do is it actually puts you, the network builder or the network owner, in the driving seat. Because now you can describe the functionality you want in your network in a high-level programming language like P4, and then compile it down to this high-performance, target processor or a target switch ASIC. So with this paradigm, you can actually describe the functionality you want. You can build the control plane on top of it, and then you deploy it in your network. And you can change it as your network grows. So this is a completely new way of doing high performance networks. Let's dive a little deeper into this fixed versus programmable packet processing. In a fixed packet processor, let me go back. In a fixed packet processor, you see all the logic is baked. You can actually see all the tables and the lookup logic is baked. There is a timer. Let me fix it. Sorry, give me a second. Okay. Sorry about that. Let's go back to the slide. Okay, so if you look at a fixed function ASIC, it has its logic baked. In this case, it can do Ethernet, MPLS, IPv4, and ACLs. If you want IPv6, you can do it. If you want to do VXLAN, you can do it, right? So this is very limiting. Now enter a programmable switch ASIC, ones like the one that Barefoot has created. In this, you have the ability to describe whatever functionality you want, and if you look in the silicon is agnostic to protocols. The silicon does not know anything about protocols. It has a programmable parser using which you can parse any protocol you want, and it has match action stages using which you can match on any field you want and look up your databases and then perform actions. So it really gives you complete control of your packet processing destiny. What are we trying to do here actually? I mean, if you look at this whole paradigm of being able to compile a high level programming language and then run it on a high performance target, this is not anything new. This has been done in other fields of technology, compute, graphics, signal processing, and most recently machine learning, where people have come up with high performance domain specific targets running code that is written in a domain specific language, which is a high level language. So now you have a very easy to program language, and then you have a very efficient compiler taking that program to a high performance target. So this actually enables a lot of innovation in any field, as it has been seen in the other fields shown here. So what did Barefoot do? Barefoot has created a couple of really innovative switch ASICs, Tofino and Tofino 2, and as you can see here, it covers a variety of bandwidths and a variety of use cases. The beauty of creating a programmable domain-specific target is you can take that same architecture and scale it up and down and solve many use cases. So we have different series of switch silicon here, targeting everything from hyperscale use cases to like service providers, including enterprise and others. So very rich set of products covering rich set of use cases. So this is the domain-specific target for networking. Now let's look at the domain-specific language for packet processing and networking. So P4 is a high-level programming language that is domain-specific to packet processing. So you will see constructs like header, table, action, key, things that are used when you're doing packet processing. So what's interesting about P4 is it's kind of becoming like the standard programming language for networking. And that's because it's fully open source, it's protocol independent, it's target independent, as well as vendor independent. And there is this P4 runtime, which is an API for devices that are controlled using P4 programs. So you have all the tools in your toolbox to basically take advantage of a high performance programmable domain-specific target. So P4 is not only for programmable switch ASICs, it can be used in conjunction with FPGAs and SmartNICs, as well as fixed function ASICs and software switches. So what P4 is good at is it's good at describing packet processing logic. It doesn't matter where that packet processing is happening, you can use P4 to describe that packet processing logic and compile it to different targets, right? Like we're showing it here. So what Tofino has done is it's created the programmable ASICs, and there are solutions in the market which take P4 programs and run them. For example, the FPGAs from Intel have a P4 compiler by a company called Netcope, and there is P4 to OVS work that is done out there, P4 to eBPF work that is done out there, and many examples of P4 being used for all kinds of different packet processing targets. This is showing the architecture of the software development environment that ships with our silicon. So when a customer gets Barefoot Tofino or Tofino 2, they also get access to this P4 Studio, which includes a compiler, a debug tool called P4 Insight. It comes with all the drivers that you need, comes with all the APIs that you need, and also a test framework. So it arms you with all the software tools you need to be able to develop packet processing logic and test it and deploy it in your network on a high-performance target like Tofino. So let's look at a few use cases. So as you know, segment routing for V6 is evolving. It's more packet processing functions are being described. And what we have done with our silicon, we were able to actually implement any new function that is described in an IETF draft literally in a matter of hours, if not a day, from the time it gets published in a draft. So here we are showing the mobile user plane functionality for segment routing V6. There's two modes, the traditional mode and the enhanced mode. So we were able to implement both of them in P4 and run it on Tofino at line rate. So this is the power of a programmable data plane and a high-level domain-specific language like P4. Another interesting use case is actually ML acceleration. So how did we do acceleration of a machine learning training workload? If you're familiar with ML training, there's a couple of ways these workloads are run. In one scenario, there's a parameter server, which is basically getting all the weights, and it averages them and then sends them out back to workers. This was how initially it started, but then it became a bottleneck because the amount of data that needs to go to the parameter server was growing exponentially. And the devices that were doing aggregation were basically choking. So now we have Tofino, which can do billions of packets per second. If Tofino can act like a parameter server, it can receive all the weights from the workers, do the aggregation in the switch, and send it back to all the workers. Now you're taking an n-square problem and making it an n problem. So in this particular case, we have actually gotten all the weights from the workers. We have done integer vector addition and then sent them back to the workers. And through this work, we were actually able to see up to 3x speed up in training workload times in the completion time. So again, another example of what you can do with a programmable switch ASIC. This is another example again of how you can use P4 and Tofino. This is a work that was done by Western Digital. What they have done is they have actually taken Tofino and came up with this new protocol called OmniExtend, which is a new approach for providing cache coherency over Ethernet networks. So they went and developed this protocol themselves, and they've actually prototyped this and then ran it on Tofino using a P4 program that they've open sourced. So again, another example where you're able to take a P4 programmable chip, create a new P4 program, and achieve functionality that's not achievable with any other silicon. So again, what can a P4 programmable switch do for you? I mean, all of these things, right? So the things that I kind of covered today are, how you can future-proof your network. I mean, all the use cases I talked about are new functionalities that are needed, and how Tofino and P4 can help you deploy those new functionalities in your network. You can reduce complexity. A lot of the times, because the fixed function chips are servicing multiple markets, they are putting features in to cover all those multiple markets. So you have code that you probably don't need when you deploy it in your network. So with a programmable switch, you can just deploy the functionality you need. And so you achieve efficiency, and you achieve lower latency, lower power, because you're only running the logic that you need to run. Telemetry is another use case. Now that the switch is programmable, and now you have a programmable way to access the metadata in this switch, you can actually export the metadata to a remote collector in multiple different ways. You can either embed the metadata into the packets as they're traversing your network, or you can create small packets that are encapsulating the metadata and send them out as a separate packet to your collector. In either case, you get real-time per packet telemetry, giving you visibility, full visibility into your network and in real time. So you can actually see what's going on in your network, allows you to debug problems quickly, allows you to prevent issues with some automation. And in the future, we will see people taking this telemetry data and feeding it to some kind of AI engines and be able to baseline your network performance and detect anomalies and do all kinds of interesting things. So we're at the cusp of this new era that we're going to enter with this packet level telemetry and AI together. Scale is another benefit. You can scale the functionality that you want because you're able to use the resources in the chip only for the features that you need. So if you take out, let's say you don't need MPLS, you don't need VXLAN. If you take out that logic, whatever resources that logic was using, you can use for your, let's say, L2, L3 features. So you get more scale. Whereas in a fixed function silicon, if you don't use that logic is unused and the resources are all tied to that logic. So not a scalable way of doing networking. So in summary, P4 is a high-level domain-specific programming language for networking, and we have created a domain-specific target called Tofino, which takes P4 programs and runs them at line rate with no penalty on performance or power or even price, because we are able to fit all the programmable logic into the same die area as a fixed function ASIC. So this will unleash a new amount of innovation in networking. Of course, high-performance networking. We are already seeing cloud customers take advantage of this. We are seeing OEM vendors take advantage of this. And through OEMs, enterprises are taking advantage of the benefits of this. So, so those are just some of the benefits that I wanted to highlight today. All right, I'll take questions if there's any.
Good job, good presentation.
Thank you.
The telemetry data.
Yeah.
How much is available information for us to collect? How frequently they come?
Yeah.
And what is missing that you may not be able to utilize if you want it?
Sure. The question is.
Telemetry format.
Sure. The question is about the telemetry data. How much is coming and how format.
Frame,
sure.
What are the different?
Sure. So P4.org has put out a spec for something called in-band network telemetry. Yeah. It's an open spec. The format is defined in it. So you can embed the metadata, after your L4 header. You can embed the metadata in VXLAN GPE. You can embed the metadata literally anywhere you want. But INT spec gives a few examples of where you can embed your metadata. And how fast this metadata can be sent depends on the target. Tofino can send it for every packet. So literally, every single packet that's coming into Tofino can embed metadata into it and then send it out. Of course, the packet will grow a little, but there is no impact to performance.
What is the overhead?
The overhead is dependent on how much metadata you're adding.
Decide.
Yes, you decide.
Is there a limit? Percentage-wise overhead?
It depends on the target again, how much you can.
What do you want?
Yeah, so there is no limit and there's no specific limit. It's just what your target can support.
And that telemetry format that you define what you are trying to send, on the other side, you need a reflective side of it to process the
Good point.
data and
Yeah.
do results, what are the delays and processing delay time and
Sure. So what you would have in a typical in-band network telemetry scenario is a source and a transit and a sink. So the source will add the metadata, transit will append to the metadata, and the sink will extract all that metadata out. Right? So all of this can be done at line rate. And now once the metadata is extracted, it needs to be sent to an analytics engine.
correct.
Now that analytics engine depends on how performant it is. It can take the data as it comes, or there could be
Accumulate.
delays. It can accumulate and do it. So we have actually created a product called Deep Insight,
Okay.
INSIGHT, Deep Insight. So this one can actually,
Deep learning, deep neural network.
it can actually ingest all these metadata packets and then visualize it and analyze it for you in real time. And it's a microservices-based architecture, so you can scale the application up or down based on the demand. Yeah. Yes?
With respect to the language, can you talk a little bit about the customizations in terms of the language feature?
Sure.
And how does that relate to the switch chip?
Sure.
Is there certain specialized data types and instructions?
Definitely.
Switch chip.
Yeah.
And then the compilation from the language into the chip.
Sure. So that's a great question. I mean, you have a high-level programming language, and you have a variety of targets. Some targets might be able to do certain things that other targets might not be able to. Like how do you take a program in a high-level programming language and map it to all these different targets, right? So P4, with its latest version called P4.16, has separated language from the architecture. So what this does, this is a very powerful construct. What this does is it allows the language to evolve independently of architectures. As a vendor of a P4 programmable target, you have to provide a target architecture spec. So all the customizations, all the interesting features that your target can perform are described in the target architecture spec. And P4 language can take advantage of those custom things in your target architecture spec, and then you can write a P4 program to compile to that particular target.
So in other systems that were extensible processors,
Yeah.
they had ways of making a sequence of instructions into a high-level instruction.
Yes.
But they were always limited by the data types.
Correct.
Where they didn't really have ways of extending the data types.
Yes.
So in yours, right?
Yeah.
Are both planes extensible?
Both planes are extensible. Yeah, so the question was, in certain languages, the data types are restricted. Even though you could change the architecture, the data types are restricted. So can we extend the data types too? Absolutely. In P4, you can extend, the language side of things, which includes the data types and all of that, and then the architecture side of things, which basically describes the targets. I mean, this is an open community, so we are actually seeing people coming in and suggest, a new data type. Or
Can you talk a little bit about the types and the abstractions, the control structures, the actual characteristics of the P4 language?
Sure.
Make it different than just building a library,
Yeah.
on top of C++ or
Exactly. So that's a very good question. I mean, if you look at any languages, like compute languages, like C, C++, the data structures and types and control structures are very different, right? For example, in Tofino, it's a feed-forward pipeline device, right? So there's no loops, there's no branches, things like that. So the constructs in the P4 language are very much like header, table, lookup, action, control, key.
data flow?
Um,
Can you think of it like a data flow language?
Yeah, kind of like that. So you describe your headers, you describe the tables, and then you describe your metadata and your parser. And essentially, when packets come in, you parse your packets, and then you map it to your metadata, and then you're taking pieces of your metadata, building a key, and looking it up in the chip, right? So this is how even a fixed function ASIC works. But the beauty of Tofino is that now you have access to all of this.
So your parser is kind of like an extension tag, right? So you build
Yeah.
your high-level grammar based on what you parse,
Yes,
right?
yes.
And then it generates it into the underlying host language,
Ex-
or base P4.
Exactly.
Oh, wow, so it's
Yep.
like, it's kind of reflective.
Yep.
Okay,
Yep.
got it.
Yeah, it's quite powerful.
And
Is
is
there,
this,
just one last question,
Sure.
is there, you know, the base is designed for Ethernet, right?
Correct.
So in the other one, the one from Western Digital,
Yeah.
they built a coherency
Correct.
protocol on top of it.
Right.
But what if, let's say we're looking at a non-Ethernet
Sure.
fabric, like for example CXL,
Yeah.
right?
Yeah.
Can you build a switch
Yeah.
for CXL using the P4 substrate?
It's a great question. The answer is yes. It will require. Yep. Oh, the question is, can you build a CXL switch instead of just a plain Ethernet switch using this language, using this paradigm, right? And the answer is yes. It will require some changes on the chip side, right? Because the chip might have some logic, like say, for example, the SerDes and other things. You might have to change those a little bit. But the match action pipeline, the programmable pipeline that I showed, has no knowledge of protocols. It is agnostic to protocols. So you define what the bits that are coming in mean, and you define what you want to do with those bits.
But then, you know, I mean, like if you look at this, the chip itself, right?
Yeah.
You said yourself that the design point was hyperscalar, right?
Yeah.
Not HPC, right? So in HPC, the characteristics, like you were at the
Yeah.
event last week, right?
Yep.
So their Slingshot is an example of an Ethernet-based protocol.
Yes.
Right, their HPC protocol.
Right.
And they talked about two things. One was the smaller data types.
Yep.
The other one was the dynamicism.
Right.
Can we build that on top of?
You will hear more. So the question was, is this, can you use this technology for HPC? The answer is yes, and you'll hear more. Yeah. One example I can give you is a work that was done by Alibaba, and they published it at SIGCOM just a couple of months ago, where they were using the telemetry feature to come up with a congestion control protocol. So they were able to actually send back information to the sender so that the sender can slow down. And so you have a very accurate congestion control mechanism, accurate and high performance or high precision mechanism for.
can you do a variable length as well from the feedback mechanism? Variable length frames.
Variable length what?
Frames in the
Frames.
telemetry.
Yeah, absolutely.
Not only,
Absolutely.
not only
The,
how
the
fast
question
you can-
is, can you do variable length frames? Yes, absolutely. Yeah.
So you just
Okay.
say, starting, you know, of the frame overhead,
Yeah.
you start, and then the end, as long as both are recognized, now the length can be more or less.
I
That's what I meant.
fully don't understand that, but it should be possible. Yeah. Yeah. Yes.
So if you consider a traditional switch,
Yeah.
so we have an ingress pipeline and an egress pipeline.
True.
We have queuing system in the middle.
True.
So can you touch base about the queuing system and the control-based system?
Sure. The question is, if you consider a traditional switch, there is an ingress pipeline, egress pipeline, and a queuing system in the middle. Can you talk about how that's done in this, in this architecture? It's the same architecture. I mean, if you're looking at doing packet processing, you kind of have to do what you mentioned. There's ingress pipeline, there's the egress pipeline, same thing. But both those ingress and egress pipelines are fully programmable. Now, what about the traffic manager and the queuing? That'll do the same things. It'll do buffering, queuing, scheduling, all of those things. So essentially, you're getting you get the same features. So with the traffic manager. Yeah, and there are ways to add more programmability to traffic manager, and those will be there too. Yeah.
One more question.
Yeah.
Say a vendor supports P4.
Yeah.
So what does it mean? For example, C, C++, right?
Yeah.
It ultimately compiles to a machine instruction. And
Correct.
the underneath chip is capable of executing those instructions.
Exactly. Yeah.
It could be x86, it could be ARM, or it could be something.
Yep.
So what does the P4 compiler provides?
Okay. The question is, what does it mean when a vendor says my device is P4 programmable, right? Is that the question? Yeah, it just means that you're able to develop a P4 program and compile it to that ASIC or target. In our case, we take the P4 program and generate the machine code for our Tofino ASIC. So we are actually able to map that logic into the resources of the silicon and do the execution. So we have VLIW engines inside the chip that are actually able to do all the actions that you've described in the P4 program. Same thing with an FPGA. You create a P4 program and you compile it to FPGA. There are compilers that basically take it, convert it into logic that can be mapped onto an FPGA.
So is there a bytecode instruction set for the execution engine itself?
Yeah, absolutely. And that is,
Register-based or it's not?
that depends on the target. That depends on who's building the chip.
Virtualization, like if you look at the CLR is stack-based, LLVM is a register-based model.
Yeah.
What's the model for the VM, or the P4 runtime set?
It will depend on the target. So,
you
yeah.
abstract that out.
Yeah, so so P4 abstracts all of that out. There's the front end of the P4 compiler that does all the syntax and semantics and all that stuff. And then the back end of the compiler is what actually maps it to the particular target. And that's where all those questions come up. Is it a register-based? Is it a stack-based? All of that, yeah.
So the backend needs to be implemented by the vendor?
Exactly. The question is, does the backend need to be implemented by the vendor? The answer is yes, because only the vendor understands how the target works. But the beauty is, one thing is, the beauty is the person who's using that target doesn't need to worry about what the target architecture is, right? They need to know a high level, but their interaction with that target is with P4 program. So that's what the power of this is, Like if you take a fixed function ASIC, you have to read the register spec. You have to understand what happens before what and what's happening after what. And then you have to see when something goes wrong, did this lookup really happen? Did this logic really get executed? In a P4 with Tofino case, you don't have that problem. You're able to actually see how your P4 program is written, so you understand the logic, and then you're able to, with the P4 Insight tool, look at how the program is mapped to your resources, and you can actually have a simulation of it and look at it, as it passes through the stages. Any other questions? Cool. Thank you.